Hey, welcome to the Explainer. Today, we're going to crack open the ultimate toolkit for anyone who solves problems using a computer. We're going to talk about algorithms. You know, those powerful step-by-step instructions that pretty much run our entire world. So, let's get that toolkit open and see what we've got inside. Okay, but let's kick things off with a really interesting question. Just imagine, for a second, that you have a computer with infinite speed, infinite memory. A machine that just instantly gets the answer to any calculation. In a world like that, would we even need to bother with clever algorithms?
Well, the answer is a huge, definite yes. Because even with all the power in the universe, efficiency still matters. Good algorithms make sure things can scale up when problems get bigger, and they save real-world stuff like money and electricity. And maybe the biggest one of all, correctness. I mean, what's the point of getting a wrong answer but just faster? And honestly, studying algorithms just makes us all better, smarter problem solvers.
So what exactly is an algorithm when you boil it all down? Really, the best way to think about it is just like a recipe. It's a super precise, step-by-step guide that tells a computer exactly what to do to get from point A, the problem, to point B, the solution. And just like a good recipe, every single step has to be super clear, and you've got to do them in the right order. And, that leads us perfectly to the number one most important rule for any recipe, or any algorithm for that matter. It has to, work. Correctness isn't just a nice-to-have feature, it's everything. An algorithm that spits out the wrong answer is actually worse than having no algorithm at all. But here's something kind of cool about that. Proving an algorithm is broken is actually way easier than proving it works. You don't need some fancy mathematical proof. All you have to do is find one single time, just one counterexample, where the whole thing falls apart. You find that one case, and you've just proven the entire recipe is bad. Let's actually see how this works. Check out this algorithm that's trying to figure out if a number is even. Let's give it the number 6. So first it checks, is 6 divisible by 2? Yep, that's true. Then it asks, is 6 divisible by 4? Nope, that's false. And since the algorithm's rule says both have to be true, it comes back with false, and incorrectly tells us the number is odd. And boom, there it is. With just one number, 6, we've broken the whole thing.
So, okay, it's pretty easy to prove something is wrong. But what about the other way around? How do you prove that an algorithm is always right for every single possible input you could ever throw at it? You can't just test all of them. For that, you need something way more powerful, a tool from the world of logic.
And that tool is called a loop invariant. The easiest way to think about it is like a promise or a safety check that has to be true at every single step of a process. It's a condition that's true before you even start the loop, it stays true after every single go-around, and because it never breaks, it guarantees you're on the right path when you get to the end. So, to make this proof stick, you've got to check 3 boxes. First is initialization. You have to prove your condition is true right from the get-go. Then there's maintenance. This is where you show that every step inside the loop keeps that condition true. It doesn't break the promise. And finally, termination. When the loop is all done, you show that your always true condition means you have to have the right answer. All right, so now that we know how to make sure our tools are actually working, let's open up that toolkit and see what's inside. When it comes to designing algorithms, computer scientists have a few core strategies, and each one is perfect for a different type of problem. First up, we've got the most direct kind of blunt force tool in the box, brute force. The name really tells you everything you need to know. The whole philosophy is just try everything. I mean, the idea couldn't be simpler, right? You just generate every single possible answer and check them one by one until you hit the right one. It's like trying to crack a combination lock by just starting at 000, then 001, 002. You get the idea. It will eventually work, but man, can it be slow. Okay, now for something a bit more clever, a lot more elegant. It's called divide and conquer. And again, the strategy is right there in the name. You break the problem into pieces, and then you solve those pieces. The whole game here is to take a huge, scary problem and just chop it up into smaller, bite-sized pieces. You solve each of those little sub-problems on their own, and then you stitch their answers back together to solve the big one. The classic example of this is a binary search, where you find something in a sorted list by just cutting the list in half over and over again. It's just worlds more efficient than trying every single thing. All right, tool number 3 is the greedy method, and its motto is basically, what's the best move for me right this second? It's all about making the choice that looks best in the moment. So with a greedy algorithm, every time you have to make a choice, you just pick the option that seems like the best win right now, and you don't worry about what might happen down the road. Think about it like making change. If you have to give back 68 cents, you're almost always going to start with the largest coin, a 50-cent piece, right? It's fast, and it often works just fine, but it's not always guaranteed to give you the absolute best solution overall.
And that brings us to our last strategy, and honestly, this one is a real powerhouse: dynamic programming. Its core idea is incredibly simple, but also kind of profound. Just remember the work you've already done.
This whole technique is built on one simple genius idea. Don't solve the same problem twice. You break a problem down, you solve each little piece just one time, and you save the answer. So the next time you need that answer, you don't have to do all the work again, you just look it up. You avoid doing a ton of extra work, and that's what makes it possible to solve some really, really tough problems.
Okay, so we've got these different strategies in our toolkit, but how do we know which one to use? How do we even tell if one is better than another? Well, we analyze its performance. We look at how it does in different situations.
So let's take a super simple example. Say you're looking for a name in a list of 100 names. What's the best case? Well, the name you're looking for is the very first one you check, done in one step. What's the worst case? It's the very last name on the list, number 100. And the average case, well, it's going to be somewhere around the middle. You can see just how big the difference in performance can be for the exact same algorithm.
Now, here's a super important point, a really common mistake people make. You might look at that chart and think, oh, the average is just halfway between the best and the worst, right? Makes sense. Nope, it doesn't work that way. The average case is all about probability. It really depends on how likely different inputs are. If you're almost always looking for stuff at the end of the list, your average is going to be much closer to the worst case.
And this whole idea of figuring out how hard a problem really is, well, that takes us to the absolute frontier of computer science, to the place where we classify the toughest puzzles imaginable. See, computer scientists group problems into these complexity classes. You've got P problems, which are the ones we consider easy for a computer to solve fast, like sorting a list. Then you have NP problems. These are fascinating. They can be incredibly hard to find a solution for, but it's super easy to check if a solution is correct. A Sudoku puzzle is the perfect example. And then you have the NP complete problems. These are the final bosses of the NP world. They're the absolute hardest of the bunch, like the famous traveling salesman problem.
And all of this leads us to one of the biggest, most mind-bending questions in all of science. What if someone found a fast algorithm for just one of those super hard NP complete problems? Because they're all connected, a fast solution for one would mean a fast solution for all of them. This is the famous P versus NP problem. It's so important that there's $1 million prize for anyone who can solve it. It's a question that could literally change everything we know about computers and maybe even the limits of what's possible.